Hello guys, so at this time you have already received back your Unit 1 exams and you've gotten your results. And chances are, if you are like most students, you're probably not super pleased with your score. First of all, let me reassure you that this is in some ways normal. This first test, I think, more even than the first quiz that we took in the beginning of the year, this first test should be some kind of wake-up call. It should give you some indication of the kind and the quality of test prep that you need to implement before any test. The kind of studying, the kind of preparation that you need to be prepared to go through. If you're not pleased with your score, chances are you didn't prepare yourself well enough. However, there's a silver lining here. What I've found so far in an AP biology class is that you're going through some kind of adjustment period. What that means is eventually you're going to become used to what this class requires of you in terms of preparation, in terms of rigor, in terms of quality of performance. And as you become adjusted in this adjustment period, your test scores will definitely improve. And I found that for all of my students last year. Okay, so I want to quickly remind you what we're going to be, or what I want to preview to you what we're going to be doing in this lecture. Chances are our multiple choice results were a little bit better than our FRQ results, our free response question results. Not only that, but at least in multiple choice you have the answer given to you on your Scantron. You have the correct answer provided. Your job when you're reviewing and correcting your test is to analyze and understand why your answer is less good than the proper answer, or why the correct answer is more correct than your answer. However, sometimes that's more difficult with the free response questions. So what I want to do in this lecture is quickly review the correct procedure to go through in the free response questions. And I didn't want to waste class time doing this, so we were doing it in a video lecture outside of class. So quickly, let's remind ourselves of scores. Multiple choice scores, you have 29 possible points, 29 questions, 29 points. So your score is a score out of 29. The FRQ, and we're going to come back to this in a second, or for each question, I'll tell you how it's broken down. But ultimately, the FRQ is worth 25 points, or both FRQ questions together are worth 25. The first question on the chi-square, that was worth 10 points. Second question on the graph about enzymes and our enzyme experiment, that was worth 15 points. So you should see on your tests scores out of 10 and scores out of 15, and sometimes scores out of 3 or 4 on subparts or subsections of each question. But on the bottom of your Scantron, you'll see an M for multiple choice and an F for FRQ. Your score under M is your multiple choice score out of 29, and your score under F is your free response score, and that's out of 25. All right, so let's take a look at some of at those two questions. First of all, number 30, the question about the chicks, is definitely a chi-square question. And so we have to immediately know the chi-square equation, even before we look at the question itself. I'm going to read the question in a second, but before we do that, let's remind ourselves that chi-square is equal to the summation, that means adding the summation of our observed results minus our expected results squared all over our expected results. Some of us had a hard time remembering this equation, and if we do not remember this equation, then it becomes very difficult for us to get a correct answer and get full credit. All right, so let's take a look at the question itself. I'm going to read it to you if you don't have, because you may or may not have it in front of you now. Number 30 says, baby chicks are pecking at grains of cracked corn of different colors. A researcher is attempting to determine if they have a preference for one color over another. He counts the number of grains chosen in an arena or an area that has equal number of red, blue, green, and yellow corn chunks. Here are his results. All right, we see the results. So we see color. All right, we're going to say red. We see blue. We see green. And we see yellow. Right? Our observed results, our observed grains of cracked corn, our number. We see 250 red, 220 blue, 230 green, and 240 yellow. All right, so in order for us to calculate our expected values, which many of us, or most of us, were able to identify the fact that we needed to calculate expected values. But in order for us to do so, we first have to sum all of these observed numbers of corn, and we get a number like 940, I believe. Okay, 940 grains of cracked corn was the total number of observed pieces of cracked corn. We have to also know that in order for our null hypothesis should be something like that our chicks did not have a preference from one color to the next, that all colors were actually pecked at an even distribution, that there was no preference for one color over another. Any differences from an even distribution would be the result of random events and random chance. So if we're looking for an even distribution, we should take this 940 and divide it by 4, because there are 4 different categories, and we should divide each category evenly. If that's the case, we should get about 235 grains of cracked corn per color, because that says that there's an even distribution between all 4 colors. Up until this point so far, I have not given you any points if you've gotten this far. All right, you don't earn points in this question simply by calculating expected values. You do earn points, however, if you calculate the chi-square for each color. And we're going to do that in a second. We're going to calculate each chi-square for each color. You will receive 1 point, okay, for a so here's a chi-square. You'll receive 1 point for the chi-square for red, 1 point for the chi-square for blue, 1 point for green, 1 point for yellow, and as we know, we're going to have to sum those chi-squares, and you're going to get 1 more point for the total chi-square. Clearly, that's not 10 points yet. You get 1 more point for your null hypothesis, for a correct null hypothesis that there is an even distribution between all colors. So that's 6 points so far, but we're not there at 10 yet. We're going to get there in a second. So let's take a look at how we calculate these chi-square values. All right, to remind us one more time, our chi-square value is equal to the summation of our observed values minus our expected values squared all over our expected values. And so when we calculate chi-square for red, we get 250 minus 235 squared, 15 squared, over 235. That gives us a chi-square value equal to, and we round it to maybe 3 decimal points or so, 0.957. We get the same value when we can make a calculation for blue. We get a chi-square value of 0.957. For green, you get something a little different. You get about 106, and for yellow, you'll also get about 0.106. We add these all together for our total chi-square. And that's something that we're going to be comparing to our critical value. We get a value of 2.13. So again, you get 1 point here, 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 plus your null hypothesis. If you've gotten all this correct, you've gotten 6 points so far. Okay, but we're not done. This doesn't tell us anything until we analyze this chi-square value statistically. So let's do that. In order for us to calculate our chi-square value, we have to figure out our degrees of freedom. And we have to remember that our degrees of freedom is n plus 1. You'll get 1 point if you get your n minus 1. If you get 1 point if you get your degrees of freedom. Because we have 4 groups minus 1, our degrees of freedom is 3. That's 1 more point that you get right there. And we know that our threshold value is a p-value of 0.05 percent doubt. That means 5% doubt or 95% confidence. All right, we need to be 95% confident that these numbers are different. And if we don't have 95% confidence that these numbers are different, then we must accept our null hypothesis. Okay, or that we fail to reject our null hypothesis. So our threshold value of p equals 0.05 gives us a critical value. If you look on your distribution table with 3 degrees of freedom, our critical value is 7.82. Important thing here, we have to say that we have to remember that if our chi-square value is greater than our critical value, then that means that p is less than 0.05, and we can reject our null hypothesis. But if chi-square value is less than our critical value, then our p value is greater than 0.05, and we must accept or we fail to reject our null hypothesis. Okay, and so what we see here in our data is that our chi-square value is less than, our 2.13 is less than 7.82. And so I should see something like that in your answer. The chi-square value of 2.13 is less than our critical value of 7.82. Therefore, our p-value is greater than 0.05. And when I ask you to estimate your p-value, I'm looking for a statement that is an inequality, something like this, that compared to our threshold of 0.05, our p-value is greater than that. And therefore, let's take a look. I'm not going to write it. Therefore, we fail to reject our null hypothesis. We must accept our null hypothesis. So let's take a look at point values here. Okay, let me change my color because I'm getting using all the same colors. Okay, you got a point for degrees of freedom. You get a point for saying that your p-value is greater than 0.05, and you get a point for saying that you must accept or you fail to reject your null hypothesis. And therefore, what that means is that the chicks do not have a preference of one colored cracked corn over another. They are, in essence, statistically choosing colors at an even distribution. Any differences are only due to chance. And so with that, we get all of our points. Okay. If you have questions about that, send me an email. We're going to move on to the next question. And this next question clearly was more challenging than our chi-square. Like I just said, this question, number 31, was much more challenging, or apparently was, than our chi-square problem. Our chi-square problem simply asks us to go through the steps of a procedure. And if we know the steps of that procedure, we're going to get it right every time. This question is a little bit more open-ended and is probably more similar to an FRQ you'd find, or a long-form FRQ that you would find on the AP exam. In fact, this kind of question, or this particular question, did appear on a previous or prior year's AP biology exam, and which is why I wanted to show this to you. And maybe you are overwhelmed with this kind of question, but it is important for us to be able to break it down and think. What I believe to be the case, likely, was that many of us wanted to go into some kind of autopilot. And we wanted to believe that this is a question that looks exactly like or very similar to questions or graphs or data that we've seen before. This is something not like what we've seen before. This is relatively different than what we've seen before, though it is related. And we have to recognize that. We have to be aware that this is something different and that we can't just automatically turn our autopilots on and answer the question like we think it should sound like. We have to be able to think, recognize something that's different, but be able to find familiarity in order to answer this question. So let's read it, please. An experiment was conducted to measure the reaction rate of the human salivary enzyme known as amylase. Amylase, we know it's an enzyme because of ACE. 10 milliliters of a concentrated starch solution and a 1.0 milliliter of amylase solution were placed in a test tube. The test tube was inverted several times to mix the solution and then incubated at 25 degrees Celsius. A lot of us focused on this 25 degrees Celsius when we probably didn't have to. This sentence right here is just a sentence that explains the procedure. Okay, it might help our responses, but it probably wasn't absolutely necessary to know. The amount of product, and I made sure to bold this, the amount of product, and I'll write this again. The product was maltose. Maltose, the thing that you graphed, was the product. Let me repeat it one more time. Maltose, the thing that you graphed, was the product, and we're going to continue to come back to that. The amount of product or of maltose present was measured every 10 minutes for an hour. The results are given in the table below. I'm not going to rewrite the results, but what I'm going to do is I am going to graph the results because Part A asked us to graph. But again, this situation is that we're dealing with amylase. Amylase digests starch, and we have to know that starch is a polysaccharide. Okay, it's a polysaccharide. We have to know that. And if we don't know that, then we're going to have issues here. Maltose, we also have to know, is not a polysaccharide. Maltose is a disaccharide. It might even be a monosaccharide, but I'm pretty sure it's a disaccharide. Point is, it's not a polysaccharide. So what is amylase doing? Amylase in this reaction is taking starch and is digesting it. All right? Just like any of your digestive system, your mouth begins the digestive process of starches. So amylase breaks apart maltose, and so maltose is a product. It is something that results from this reaction, and we have to be aware of that. We have to recognize that in order for us to have an understanding and awareness of what these data are trying to tell us. So let's graph these data. Okay, so part A tells us to graph the data on the axes provided and calculate the rate of reaction for the time period 0 to 30 minutes. So part A is asking you to do two things: graph and calculate. Some of us just graphed and didn't calculate. Some of us, and we'll talk about what it means to calculate the rate of reaction. It's not very difficult, but let's graph first. So we know that we're going to need two axes. I'm going to undo this actually. Undo. Okay, I moved our axes over so that we can label them. Some of us didn't label our axes. What I'm looking for in a graph is properly labeled axes, properly titled graphs. Many of us forgot a title or didn't title it correctly, and I'm looking for proper data. All right, so our x-axis here. I'm going to turn this into a black marker now. Okay, so we know that we're looking at time here, and it's simple because we go from 0, 10, 20, 30, 40, 50, and 60. Our x-axis is time in minutes. Easy. And we have 10, 20, pardon the marker, it's not very thin. I can make it thinner. 30, 40, 50, 60. Obviously, the graph here is not going to be perfect. So many of our graphs look much better, and I appreciate that. Okay, on the This graph is telling us how much maltose is being produced. Maltose is a product. It is an end product. Okay, and that's going to tell us a lot about what this graph is saying. So let's graph this. At 0 minutes, I'm going to graph it in red. In 0 minutes, we have 0. At 10 minutes, we have 5.1. Okay, that's not really 5.1, but it's close enough. 20 minutes, we have 8.6. 6, 7, 8.6, somewhere around there. 30 minutes, we have 10.4. Close enough. Yeah, not the best. 40 minutes, 11.1. Okay, we're about maxed out here. 50 minutes, 11.2. 60 minutes, 11.5. And let's connect our dots, and we see that this graph levels itself out and into infinity. Okay, this is huge. We have to be able to understand what this graph is telling us. But before we do that, this question asks us to calculate the rate of reaction. Well, any rate of reaction is a magnitude over time. It's how fast something is happening. For example, your rate of velocity when you're driving your car, usually given in miles, is a magnitude. Per hour is a time. Magnitude over time is rate. If you did not give me a quantity that had the units milligrams, this is also, micrograms. It's a micrograms per minute. I didn't take points off, but you should have, and you would have gotten points taken off on an AP exam because you didn't tell me anything. If you don't have units, your numbers are worthless. Okay, micrograms per minute. So we have to ask ourselves, after 30 minutes, how much maltose did we produce? Well, we look at that value, we see 10.4. That is to say, we see 10.4 micrograms per 30 minutes. All right, I needed to see a number that has 10.4 over 30. All right, let's take a look at point values now. You got, I'm going to turn back to green. You got a point for your rate. I took a lot of points off of title. You get a point for a good title. Essentially, you get 3 points for a good graph. If I found 3 things that were wrong with the graph, that clearly wasn't a good graph. Some of us got 1 point, some of us got 2 points taken off on our graph. Some of us didn't scale our axes, some of us didn't label our axes, some of us didn't include units on our axes, some of us didn't really graph our data properly. Okay, so you get 4 points in total for part A. Okay, so let's take a look at part B next. Part B asks us to explain why a change in the reaction rate was observed after 30 minutes. Well, we said that the rate was 10.4 micrograms per 30 minutes, or 10.4 over 30 micrograms per minute. And after 30 minutes, we see a leveling off. Okay, but many of us said that the reaction, or that the enzyme, was working at its maximum potential. Okay, but we have to remember that maltose is a product. And so we have to ask ourselves, after 30 minutes, or rather, let's say at 0 minutes, did we have lots of maltose being produced? Yes, because between 10 minutes and 5 minutes, that slope of that line was very steep. Between 10 and 20, we see more maltose being produced. That means the enzyme is working. It's working quite quickly to produce maltose. Between 20 and 30 minutes, we start to see some slowing down of maltose production. That means the enzyme is slowing down the process of breaking down starch. After 30 minutes, that process of breaking down starch is almost over. Maltose is no longer being produced. In fact, the enzyme itself is not working at a maximum rate. It's almost not working at all. It's working at a near 0 rate. Because if we know anything from calculus, perhaps, we know that the rate of a graph is the slope of that graph, the derivative of that graph. And we know that if the derivative is horizontal, that means the rate is 0. Which is to say that the rate of reaction, or the rate of enzymes working, is almost near 0. And we have to ask ourselves, why? Explain why. Well, what does it mean that the enzyme's not working anymore? What does it mean that maltose isn't being produced? Well, the answer then becomes clear. Maltose isn't being produced anymore because there's no more starch to produce maltose. The enzyme isn't working anymore because it's already catalyzed all of the starch in the reaction. The reaction's done. All right. If you said something like the reaction's done, there's no more substrate to break down, then you got some points. All right. That's what we need to see in part B. Now again, part C was another tricky one because it asked us to do something that we haven't done before. And that's what most good tests do. They use information that you already have, use knowledge that you already have, and apply them to new situations. It tells me, as a teacher, can you use your information? Can you wield your knowledge? Some of us have a hard time doing it at this point. We're still adjusting. But let's quickly redraw a basic pattern of our graph. We know 10, 20, 30, 40, 50, so on, 60. And we see that the data in our graph goes something like that, okay? Where this is 30, 20, and 10, okay? And this is about, we said 11 or so. Okay, part C asks us to draw and label another line on the graph to predict the results if the concentration of amylase was doubled. Let me repeat that. Amylase is doubled. That means we have twice the amount of enzyme. But did it say anything about starch? No. Did it say anything about maltose? No. And remember, our y-axis depicts maltose. That's a terrible way of writing maltose, but that's what it is. We're talking about maltose here. Maltose didn't double. So our graph should never go anything higher than where it already is. We're not using more starch. We're not producing more maltose. We're just adding more enzyme. And we should know from our lab, stuff that we've already known, stuff that we've already calculated, that when we increase the concentration of enzymes, that we're increasing the rate of reaction. And we already know that we calculate rate by calculating slope, all right? By calculating magnitude, amount, over time. Magnitude over time is slope. A steeper slope means a greater rate. Okay, so if we see if we have more enzyme and we know that more enzyme means faster rate, then our rate should become steeper. And if we've doubled our enzyme, we should see that at 15 minutes, half of the amount of time, our rate should level off, and we should have finished the reaction in twice the amount of time, because a shorter amount of time means a faster rate of reaction. Let me repeat that one more time for those of you who didn't get it. Okay, we've doubled enzyme. We've not doubled substrate or product. So our line should stay at the same level, 11 micrograms or so. Because we've doubled enzyme, we know that more enzyme or greater concentration of enzyme will increase the rate of reaction. If we increase the speed of reaction, that means that we will finish the reaction in a faster amount of time. We've doubled the amount of enzyme, so we should finish the reaction in about half the amount of time. That is to say, at about 15 minutes, we should see the enzyme we should see the maltose leveling off, because that indicates the end of the reaction. Think about it this way. If I have a certain amount of ingredients to make pizzas, I can make pizzas at a certain rate, and eventually I'm going to run out of my ingredients, and I will have made 20 pizzas. All right? I can't make any more pizzas because I don't have any more ingredients to make it with. Okay? And maybe I make those 20 pizzas in 10 hours. However, if I increase my workforce if I double my workforce, I can cut my time in half. I'm not making any more pizzas, but I am working faster to make those 20 pizzas. I'm working maybe in half of the amount of time. Okay? So you got some points here. In part B, I forgot to talk about part B. You got some points in part B if you explained that you ran out of substrate and that the enzyme finished the reaction. In part C, you got more points. You got 1 point if you drew a line that had a steeper slope. You got 1 more point if that line finished at about 15 minutes and didn't go over 11 micrograms. You got 2 more points if you explained properly why. Many of us got this point. Almost none of us got this point. Some of us got 1 or 2 of these points. Okay, so that's just to take a look at that. All right, so and then in part D, it talks about 2 environmental factors that can change the rate of an enzyme-mediated reaction. All right, let's talk about this in black. 2 more factors, 2 more variables, 2 variables that we should have written a procedure on, and some of us didn't write procedures on them because we didn't really do our homework. And it really pays in our test. So many of us didn't get these points or didn't get all of these points. Many of us said temperature. Oops, sorry. Let's try this one more time. Many of us said temperature. Temperature is great. You can say that temperature will increase the rate of reaction. Or rather, increased temperature should increase the rate of reaction. And I asked you to discuss how each of those 2 factors would affect the reaction rate of an enzyme. If you said increased temperature increases the rate of reaction, I gave you 2 points, one for indicating temperature and the second point for telling me how that affects the rate of reaction. I really wanted to ask why, but we really didn't get into why temperature increases the rate of reaction, and we can talk about that later. Another variable that you may have chosen would be maybe salinity, because we talked quickly about salinity. Salinity meaning salt, and salt being an ionic compound. If we increase the number of ions, then those ions will change the interactions and the bonding of those R groups in the amino acids of that enzyme. And if we change the bonding pattern, we change the folding pattern. If we change the folding pattern, then we change the active site likely, and maybe we denature that protein or that enzyme. And if we denature that enzyme, then we're likely going to slow the reaction down. So increased salinity will likely decrease the rate of reaction. In fact, it might even stop the rate of reaction because it would denature the folding pattern of that enzyme. We could say the same thing about maximum temperature. If we boiled our enzyme, we'd probably add too much energy, disrupt the folding pattern, and denature. Same thing can be said of pH. Increased pH would likely, or rather decreased pH, increased acidity would likely decrease or inhibit or impede the folding pattern of that enzyme, denaturing the enzyme and therefore decreasing the rate of reaction. Those are all things that you may or could have said, and that brings us, you would have gotten 2 points, 1 point for each for identifying a variable, another point each for telling me how it affects the rate of reaction. This total question was worth 15 points each, and you have a point value for each, or you have a score for out of 15. So, we've gone over the 2 FRQs at length. If you have any questions about these FRQs, please email me and we can talk about them. Thank you.